record. All right, looks like we're recording. This is, of course, Canvas screen, and Wednesday, one more week in the semester before we go to a reading day and then final exams. We'll talk more about the final exam next week, but the format for it is going to be very similar to the second midterm. You'll do it on mastering. But here are the last four worksheets. You can see we're now in chapter 34, I guess. Is that correct? Nope, I'm sorry, it's worksheet 34. We're in chapter 31, okay? And so we got two worksheets in chapter 31, displacement currents and electromagnetic waves. And then we're gonna obviously start talking about optics, because an electromagnetic wave, a special case is light, and we'll work a little bit of light. Wish we had more time, wish we hadn't lost that week after spring break. I'm not going to be able to talk about mirrors and lenses this semester, but I think you'll get a taste of physical optics, interference, diffraction gratings, and then reflection and refraction. So we'll talk about a couple of the topics, okay? This is all spread out in our textbook over four chapters, actually, 31, 33, and 34. 32 is the lenses and the mirrors, something that had to fall off. We just didn't have time for that because of the lost week, even though I tried to recover a little bit, but I hope that's okay. If you need that for your capstone down the road, or you're interested in that, I can always recommend things for you to do, but we just won't have time for it this semester. Okay, so there'll be one more homework assignment in mastering. That'll be the last homework assignment. I see it due sometime next week. I did put up another assignment for chapter 30, the Faraday's Law chapter, the induction chapter that we just finished. I've got that due, I think, 27th. Today's the 20th. Would be due next week, okay, is 27th, and then the final one on chapters 31, 33, and 34 will be due probably on the reading day is when I see that. So that's the work for the rest of the semester, and we'll be putting a bow on it and drawing it to a close. Now, I want to shift gears here. Any questions on any of what I just said right there? Administrative stuff. All right. My plan, by the way, on the exam is to have the exam available to you sometime around Tuesday of exam week. Our normal exam for this class will be Thursday, and so the exam will be due on Thursday. It's same format as before: open book, open notes, open resources. The only thing you can't do is talk to another human being, and that's either electronically, that's face-to-face, that's in a chat room, that's anyway, no talking to another person. It has to be your work. If you find a solution to a problem somehow, good for you, and that's great. Questions on that? All right, moving on then. Here's what we're going to be talking about next. And stop sharing Canvas, start sharing PowerPoint. If you take a class in physics and you tell somebody you were in the second semester of a physics class and they've got some awareness of what happens in physics and science, they say, oh, well, then you know all about Maxwell's equations, because at various times through the semester, we talked about all of these four equations right here, which have been named after James Clerk Maxwell, who really didn't have a whole lot to do with them other than one thing we're going to talk about today, and yet he kind of gets credit for all four. If you think way back, we talked about Gauss's law as a way of finding the electric field, and I wrote a wacky equation like this. It's funny, I don't know how many of you might have happened to have taken multivariable calculus. I know everybody is in the integral calculus, has some differential calculus. I don't know how much the math people have given you notions of, hey, how do you move beyond one-dimensional mathematics calculus problems? And hopefully in physics, we tell you that how important that has to be. How do you solve a one-dimensional world? It's even hard to solve a two-dimensional world sometimes, because we live in three dimensions, and that's why this integral over here is over a volume. Now, it doesn't have to be. And if this weirds you out, if you don't like that, in our class, this density here is always going to be a constant. So this thing right here in our class is just the density times a volume, right? You have to know what the volume is. You have to know what the volume of, say, a sphere is or a cylinder is. But that's all that's going to be, because that is charge charge enclosed in some volume, and that's why we're writing this. Okay, and on the other side, this kind of weird integral, that always turned out to be E times some surface area. And truthfully, even without understanding the calculus, if you know the rules for what A is, which is how I did this in high school. I mean, I didn't know any. I took taking a little bit of calculus. I wasn't an AP kind of person, but we just got taught E times A is equal to Q over epsilon 0, and we were able to do the problem. But the full, if you understand some calculus, the full-blown equation looks like that. And in physics, when we write things out like this, we're often looking for patterns. Okay, and so that was Gauss's law way back. And then we talked about Ampere's. I'm sorry, let's wait on Ampere. We talked about Gauss's law. I saw the magnetic field and I jumped right away. Gauss's law for magnetism. One of the things that's troubled physicists is the difference right there, right? And we talked about the fact that if you cut a bar magnet, you can't take away the north and the south pole separately. When you cut a bar magnet, you create two more magnets, because unlike charges that you can isolate individually, you can't do that with the poles of magnets. Interesting. There's an asymmetry in nature here that has bugged scientists to today. People are still looking for that north pole by itself without a companion south pole that's analogous to a positive charge without a negative charge. It bugs us. Okay, lack of symmetry bugs scientists. We think we must be missing something because we expect the world to be symmetric, and that's a reasonable expectation sometimes. Me personally, I think there is no such thing. I think I'm gonna go to my grave never having heard of magnetic monopoles, although there is serious research in science looking for them today and being funded with big dollars. Okay, so then we talked about Faraday's law. We just finished that up, and we said, well, this is all electromotive force right here, right? Volts. It's electric field, and we did one problem where you had to figure out what the electric field was when a magnetic field might be changing. So the changing flux exists, and we expect a current to flow, but if a current's going to flow, I guess, why is the current going to flow? The current's going to flow because there's an electric potential. Okay, that's the electromotive force. Well, if there's an electromotive force, if there's a potential, there must be an electric field that exists, even if it's just in free space, even if it's just in a piece of metal. We talked about eddy currents, okay? But the point is, electromotive force is the change of a magnetic field over an area, so that's a magnetic flux in time. And that negative sign there is all about Lenz's law. Lenz figured out that for a lot of, I guess, entropic, if you understand entropy, things, you can't create perpetual motion, right? The current that's produced has to oppose the change which created it. If it aided the change which created it, all of a sudden you'd have a runaway perpetual motion sort of current, and it would just get bigger and bigger and bigger, and that just makes no sense. And so that is the meaning of that negative sign. And I've told you, when you're doing problems, more often than not, ignore it, okay? Find the magnitude and then assign direction based on your knowledge of Lenz's law. Okay, so this is a great law. We've had a lot of fun with it for the last week, at least I have, and I hope you have as well. But we look back and should compare it, especially when I added this part, which again, we only did one problem on the worksheet on that. Get out of there, go away. The magnetic field gets integrated in exactly the same way around a closed loop. And we said, well, I could calculate the magnetic field. And remember this, again, don't make much out of this. This is going to be the magnetic field times some perimeter, more often than not, a circular perimeter, a circumference. And then all I have to do is figure out what the current inside is. And it does bother people, and it bothered people in the late 1800s at the time of James Clerk Maxwell, that those two things look so similar. Just swap the electric field and the magnetic field, swap the electric field and the magnetic field. And all we had was a current, and it just seemed like there's something missing here, okay? And that is the work of Maxwell. Oh, great. Thank you, Comcast. I was probably breaking up there a little bit, so I'll slow down. And we're missing something right here. And maybe you could go the other way. We're missing something right here in Faraday's law. There's no constant times a current. Anyway, that is the work of today's lesson, predominantly, certainly the worksheet today, problems with Ampere's law, okay? B times the circumference is equal to mu 0 I, but if you compare it to Faraday's law, there's something missing. And so that's the question. And here's the paradox, I guess. When we said this current had to be enclosed by a surface, and see it's shaded kind of in brown, there's the closed path that has some circumference 2 pi times whatever its radius is, right? So I got a radius right here. That's what we're talking about. And this is the current, which we said was going through the surface area enclosed by that path. If I had 2 wires, I'd put 2 wires worth of current. Sometimes we had one going one way, one going the other. They cancel each other out. You worked with those sorts of problems. Most people did it successfully. Did we specify that it had to be the smallest area? Think about, the little wand you had to blow bubbles when you were a kid. You put the bubble wand into the bubble thing, you pulled it out. The soap film took the smallest surface. It took surface 1 until you either moved it through the wind or you blew on it, and then it changed to surface 2, which is okay. It's still a surface 2 here, bounded by this path, right? And look, the same current goes through that surface as well. We never had a requirement that it be the smallest surface bounded by the path that has current going through it. So surface 2 is every bit as legitimate, okay? And hopefully you got the picture of the bubble in the little wand. You had the little circular wand to make bubbles. Any event, either one of those surfaces would cause us to do what we said. This thing right here, which I'm sure everybody hates looking at, just becomes B times 2 pi r. We say it's mu 0. In this case, whatever this current is goes right there as the current enclosed. And sure enough, we solve for the magnetic field equation that hopefully you've used for long straight wires over and over again. And then really the only thing, once you've got that magnitude of the magnetic field, is, well, what direction is it? We had a right-hand rule. If your current is moving to the right, you put your thumb that way, your fingers swirl around in the direction of the magnetic field. And so I guess it's out of the page up at the top, right? Let me make sure I got that right. And swirls around the front, and then it's into the page right there. And then I can't draw it anymore. I can kind of maybe dash it around the back, and that's the direction of the magnetic field. So this all works really well. Okay, that's not the paradox. The paradox is coming right here. What if, and we've studied these, what if along that line of current right there, we slap in a capacitor? Did it in my basement lab, not this week, but I guess 2 weeks ago, right? Put a little capacitor, that's all that a capacitor is. And I can see here that there's that surface 1 I talked about, the smallest one, the surface area that soap film would take on your bubble wand, I guess. But there's another one back here, you notice, that is every bit as legitimate as this one over here, right? Surface 2 over here. Oops, going the wrong way, sorry. But you notice, where is that surface right there? Okay, surface 2 now, I've kind of made it a little bit bigger, and I let it go right between the plates of the capacitor. And so now, both legitimate surfaces. This is the paradox. There is current going through surface 1 right here, clearly penetrating right through that surface. It would pop your bubble film if it was a real thing, okay? But over here, this second surface, which is every bit as legitimate, has no current going through it. But as the capacitor either charges up or discharges, there is an electric field that is changing because the charge on the capacitor is changing, right? So while it's not sensing current, because there is no current going through that surface 2, there is a changing electric field going through surface 2. There is a changing electric flux through surface 2. And so that is a problem. The paradox, of course, is if I just try to employ Ampere's law, well, this side right here would be exactly the same. But as I said, for surface 2 here, for surface 2, there's no current. And so if you use surface 2, your conclusion would be that the magnetic field was 0, and you'd be wrong. Okay, you would be wrong. So there's something missing. And this is what James Clerk Maxwell figured out, what's missing. And it's related to, well, there is a change in electric field. So it's either increasing or decreasing, depending on whether the current is delivering more charge to the capacitor or taking charge away. Okay, their internet connection unstable, probably breaking up. Okay, we'll give it a second to heal itself. Okay, in any event, there is an electric field, there is an electric flux, and it's changing. And somehow that must be equivalent to the actual current that's going in this wire right here. that must have the same effect of creating a magnetic field. And that's what Maxwell just figured out. And it's just, we call it his correction to Ampere's law. And you got to go back with some equations that we knew back in the capacitors chapter. The amount of charge that I'm showing right here with these little pluses and minuses on a capacitor is equal to the value of the capacitor times the potential that's across the capacitor. And let's see, the capacitance for a parallel plate capacitor, we said was the permittivity of free space, the cross-sectional area, and divide by whatever the separation D is right here, right? So there's D, there's A. That's what we said, and it's only one A. It's either this side's area or this side's area for a parallel plate capacitor. I've often seen people try to combine them, get the total A. No, it's just area of one of the plates is the meaning right there. And of course, potential here, I just wrote it in a real highfalutin way. I said E dot ds, right? And I was going around a closed path in I guess Faraday's law, but just more often than not, if the electric field is a constant, it's just electric field times some displacement within that electric field. That's the potential. And if you put those two together, I guess you'll notice the separation here cancels. That's why parallel plate capacitors are so instrumental and understandable, is because everything's so linear and you can just cancel things really nice. Okay. And what are you left with? Well, I guess I got this guy right here. And that's a field times an area. Hey, that's a flux. Go figure. That's an electric flux, right? And again, if it weirds you out that sometimes I write it like this, and I even went two integrals, because this would be like a dx dy, right? And it's over some maybe a closed path or not, okay? That's just a flux, a field times an area. If the area happens to be a closed surface area, like I don't know, a sphere, an obloid sphere, it's a football, it's a soccer ball. If it happens to be closed, we put this little symbol on the integral side. Just a flux, okay? So the charge here, apparently, on the capacitor is equal to the permittivity of free space times the electric flux. And of course, remember what our definition of current is. Current is the rate of change of this charge right here. And permittivity of free space, that's a constant in nature. Derivative of a constant is just it just slides right by, right? We don't worry about that, but we do have to take the derivative of the electric flux. Okay, so apparently this thing right here is equivalent to a current, and so Maxwell chose to call it displacement current, and we subscript it with a little d here, right here, to denote that it's the displacement current. It's not real physical amps, charges moving in a wire. It is a current equivalent to the current moving in the wire that is caused by a changing electric field right here, or a changing electric flux that's happening over time. Okay, and it apparently is going to cause a magnetic field for us and resolve our paradox. So let's kind of see how that would work in this equation. Okay, I just took that little parenthesis, that little question mark, I guess, that I had, and I jammed that right here. And I also had to multiply by the constant, the permeability of free space. It gets multiplied by the actual current. It must also get multiplied by this displacement current right here. Okay, and so I guess I've written out this a little bit to see the pattern, I guess. I wrote it as J times dA, because remember, J is equal to the current divided by the area. And so if I bring the area over to the other side of the equation, I can replace I here with J dA. And the reason I did that, of course, is because electric field times dA is an electric flux. And so I wanted to see the relationship here between an electric field, which is changing in time, and a current density, which is not. But I could slap them both inside the integral. And apparently that's equivalent to a magnetic field in Faraday's law changing. And now these are starting to look a little more symmetric, these equations. I still haven't done anything with the fact that we have this asymmetry in nature, that there's no magnetic monopoles, but I've made Ampere's law look a lot more like Faraday's law by the addition of this displacement current, the idea developed by James Clerk Maxwell. Okay, it gets even more symmetric if you go to this place called free space. Now, free space is a term of art in physics. It's not around any matter. There's maybe you consider a vacuum free space. Out in outer space would be free space. And, there's no charges running around. Maybe at least not a very high density of them. I don't know if we can ever create a place where there are no charges, but there's certainly no wires, and so there's no currents. And so if you take the previous slide, in every place there was a free charge or a current. Thank you, Comcast, for the third time I'm probably locking up here. Get rid of those, I guess. Now you can see these two equations right here look a whole lot more symmetric out in free space. Gauss's law and Gauss's law for magnetism have a pretty similar form out in free space. In fact, just swap the E and the B, right? The electric field and the magnetic field replace each other, and they look a whole lot alike. And again, if this bugs you, just ignore it for now, okay? Faraday's law, an electromotive force being the negative of the rate of change of a magnetic flux, and Ampere's law with Maxwell's displacement current looks exactly like Faraday's law. It's just I've swapped the meaning of the type of flux I've got here, and I've swapped the field which is created. Okay, and the difference is in this case, the constant is -1 out front here, and here the constant out front is the product of the permeability of free space and the permittivity of free space. Two constants we've used throughout the semester, right? 8.85 times 10 to minus 12 Coulomb squared per Newton meter squared for permittivity of free space, and permeability of free space, 4 pi times 10 to the minus 7th. I like Newton per amp squared, but other folks have different units on that. I find mine to be the most handy. In any event, you can see the symmetry there, okay? And it has important consequences for where we're going next in the course. And none of this would be possible without Maxwell realizing that something was missing, this so-called displacement current, which, by the way, is the complete subject of the worksheet that you'll be doing for today, investigating displacement current, actually calculating it, and see how it's absolutely equivalent to a regular current in a wire. Okay, so that's that. None of this would be possible without Maxwell figuring this out. All right, so here's the implication, and this is the importance of it. Let's say we got a magnetic field produced in empty space because somehow you change an electric field, okay? Because that's what we're predicting, right? If I change an electric field, I change an electric flux, that creates a magnetic field. That's what that equation is telling us. It has to change in time, but if it is, okay, we've created an electric field. And what I've done here is I've kind of came up with what was probably the most rudimentary way to create a change in electric field. Let's have a battery and a couple long wires coming out of it. Shut the switch. All of a sudden, I'll have current flowing, at least for a short period of time, and I'll create an electric field. And because there was no electric field before the switch was shut, it's a change in electric field. It's not going to last very long, but it changes. That change in electric field is what we say creates the magnetic field according to Ampere's law. Okay, now that means a magnetic field will be created when there was none. So that's a changing magnetic field. Okay, originally there wasn't one. The changing magnetic field is going to come back to produce an electric field. That electric field will be changing. Okay, and that produces a new magnetic field, which is changing. And that magnetic field is going to create an electric field, which is changing. And so what I'm pointing out here, I guess, is that this original change in electric field creates a magnetic field, which is changing. And that creates a magnetic flux in space, which is changing, okay? And that creates an electric field, which is changing, and that comes all the way around here and creates an electric flux, which is changing, and you can see these two equations just bounce back and forth off of each other, creating alternating, changing electric and magnetic fields. All right, and hopefully this looks to you like something you've seen less these days. We've found efficient ways to make antennas less and less visible in our lives, but they're still out there. Every radio station has a big antenna, which is just this long piece of metal sticking up in the air, right? We still have them on some older cars. You notice more and more new cars, the antenna is put in the windshield of the car, is some grid magnetic, metal grid that's put in a windshield. So we're less and less aware of these antennas, but that's what we're doing. We're creating changing electric and magnetic fields with these antennas, or on the other hand, maybe detecting changing electric and magnetic fields from something called electromagnetic radiation. All right. And by the way, I think it wasn't long before people got tired of that switch which opens and shuts. And we talked about generators which create a voltage which is oscillating sinusoidally. We talked about that as one of our problems in Faraday's law. And, people were doing that in the late 1800s. It wasn't long before we got rid of that battery and a switch that we opened and shut and put in something that was constantly changing voltage and current. An AC source is what we call it, alternating current source. And so that's going to create current that changes direction here, which is certainly going to create changing electric fields, which create changing magnetic fields, which creates changing electric fields. And all of a sudden, we find that this thing moves away from the source, okay? It's called a radiation field, and it's moving away. All right, let's take a look at like along one line. I say look at the cross section, but I'm thinking about it's traveling in all directions. I'm just going to follow that direction right there. And if you look, I have initially a magnetic field, I guess is the way I started this diagram, going into the page. So that must be because current's going out. And then as that changes, I get an electric field which swirls around, and that creates a magnetic field coming out of the page, and that changes, and that creates an electric field that's swirling in the other direction. And if you kind of look straight below right here, I've graphed what I hope along that kind of crooked line I've drawn here. See, there's the magnetic field going into the page, and the electric field right there is downward, so it's drawn that way. And then next to it, where these changes create fields out in front in space, I've got the magnetic field coming out of the page here, and now look, the electric field is going upwards. And then right about here, things start to change, and now I've got a magnetic field going into the page, and then the electric field is coming down, and all of a sudden it looks sort of sinusoidal perhaps. If we started with an alternating voltage, alternating current source, we're going to get magnetic fields and electric fields that are changing in a sinusoidal fashion as well. Okay, a couple things to observe about what I just said there. We said that the electric field and the magnetic field in this particular orientation with the antenna, I've drawn it really small right here, the antenna oriented vertically, the magnetic field is either into or out of the page, and the electric field is either up or down. The electric and the magnetic fields are perpendicular to each other. The word we use for that, we say they're transverse. The other thing I would say is that they're in phase. We notice that when the electric field is zero, the magnetic field is also zero at those same points. And I tried to line these two diagrams up. They weren't necessarily meant to be that way, but hopefully you can see those points right in there where the electric and the magnetic field both go to zero. On the other hand, they both reach peaks at exactly the same point as well. Internet connections unstable. I'm glad it warns me. Hopefully you caught some of that. So they're maximums at the same point right there. That's why I've drawn lines closer together and field lines closer together. Okay, electromagnetic radiation. I want to jump out of this for just a second because I have a little animation to show you about this. And so let me share back over to share Canvas for just a second, and then I'm going to go over to an active figure that I've got. Let me make it a little bigger. And these are those, and one of the things I like about the textbook I stole these from is there's a color coding, right? If you remember on the previous diagram, B, the magnetic field was in blue, I guess blue for magnetic B. And then the kind of orange is red, whatever color you're seeing there, and more yellowish orange right now, that's the electric field, okay? And if I resume this thing, you'll see that the magnetic and the electric fields kind of travel in the direction where I've shown the speed. We're going to call the speed of these waves C here in a second, the speed of light, okay? The speed of an electromagnetic wave in a vacuum, okay? And if you can kind of see two pictures developing that I want you to think about in your mind. One is, if I just took a snapshot, I went pause, okay? Well, most people trace the electric field because the numeric magnitude of it is bigger, the amplitude of it is bigger, and it's just going to turn out that way. Magnetic fields, remember, we said a Tesla magnetic field is huge. So to avoid having those powers of 10 for normal sized magnetic fields, we just don't try to talk about them. We typically talk about an electromagnetic field, we're referring to the electric field portion. We recognize that the magnetic field's always there along with it, and we'll show you how the two compare in amplitude here, either today or on or on Friday, because we'll continue on with this discussion on Friday. But hopefully you can see that's one view, okay? And I'm going to show it, I'm going to graph it here in a second. I take a snapshot, okay? The other view I want you to think about is I put a little sensor right here at some position X, and that's what's being shown here, what happens over time as the wave passes that sensor. And you can see it alternates sinusoidally as well. And so I suppose if I was trying to graph this, I could graph in time a sinusoidal electric field or a sinusoidal magnetic field. But again, people default to drawing the electric fields. And that's exactly what I'm going to do. Recognizing that doesn't mean the magnetic field isn't there. It just means it'd be too complicated to draw in that third dimension. And so we just draw the electric field. It's presumed the magnetic field tags along. Don't ever forget it's there, though. Has to be. Otherwise, the electric field wouldn't continue to propagate, wouldn't continue to change. You need Faraday's law and Ampere's law bouncing back and forth against each other to make the magnetic and electric disturbances travel through space. Okay, everybody good with that picture? Any questions on it? All right, well, apparently if I got these things now, I got to go back and review a little bit. Come on, share. I got to go back and review some of the stuff we talked about back in the waves chapter at the start of the semester. Okay, and good, got that. All right, and so we talked about plane waves. This is actually a slide I took right out of, I guess it's chapter 15 and 16's notes when we were talking about mechanical waves, disturbances in, say, ropes or springs or the tabletop, if I was moving a wave down the top of a table. And this is the picture, the snapshot when I froze the wave, okay, and I plotted what the displacement was for the mechanical wave, but now I'm plotting what the electric field is. And just a couple words we used back then. If I go from that point to that point, we call that distance in space lambda, the wavelength. Some people call it the spatial period. By the way, it doesn't have to be from zero crossing to zero crossing, because that sometimes confuses people because that's a zero crossing. If you like, there's a wavelength as well right there from two crests, two peaks of the oscillating electric field, right? That's a wavelength as well. On the other hand, remember, if I put that sensor at a location, that arrow I had, as the wave moves by, and I plotted what the electric field looks like as a function of time, it would also be oscillatory. You saw those vectors growing, going, changing direction, growing, changing direction. And if I plotted it, it would look like this. This interval in time over which the wave repeats itself, we refer to as a period. And of course, if I'm going to call this a space period, a spatial period, I might want to be more specific and give this an adjective too, call it the temporal period. But more often than not, people just say period and wavelength. Okay, why is that important? Well, we said there was this velocity for these waves. It was true for mechanical waves. It's true for these electromagnetic waves. If you take the distance that the wave travels over one cycle, which is a wavelength, and you divide by the time it takes to go through one cycle, well, that must be a speed, right? And we said that the frequency, this number in hertz, how many cycles it completes per second, well, even just as I said those words, that has to be the reciprocal of the period. So you can write the speed of the wave as the frequency times the wavelength. And then one other thing we did when we were talking about mechanical waves, which is still true for electric waves, is I multiplied by 2 pi over 2 pi, because that just multiplies by 1. I haven't changed anything. And I realized if I separate these out, the 2 pi over the period, we call that omega, the angular frequency. It's related to this guy, right? I think, let's see, frequency here would be omega, but I divide away 2 pi because there's 2 pi radians in every cycle. If F is cycles per second or hertz, and there's 2 pi radians in every cycle, well then radians per second divided by 2 pi radians becomes cycles per second, and it becomes frequency again. So that's what I did there. And then there was this other thing we had when we had traveling mechanical waves called a wave number. And the wave number is just 2 pi times the wave divided by the wavelength. And so you can see I've got the reciprocal of that right here. And so omega, the angular frequency, divided by the wave number must also be a way I can calculate the velocity of this wave. Okay, and so that's just a little bit of a review of plane waves from back in mechanical waves. Everything I said there is completely true. If you learned it back in chapter 15, 16, I believe, it's still true in chapter 30, what are we on, 31 here. Okay, now this is a little wacky, and if any of you have taken multivariable calculus, I have to tell you, one of the things that always bugs me is I can't look at your transcripts to know if there's anybody out there who's had that course. It just isn't allowed in our system. And I'm used to being able to look at your transcript to know. So I don't. But there's a thing called there's two integral theorems that you learn in a multivariable class, divergence theorem and Stokes theorem. They're part of a mathematical theory, Green's theorems. They're subsets of Green's theorem, and they allow you to convert, interesting enough, between integrals and derivatives. And we need to do that without that mathematical apparatus in place. And so I'm going to take a look at this traveling wave, and I'm just going to do the operation as best we can and see if we can get from, let's see, this is Faraday's law, okay, rate of change of magnetic flux is related to an integral, because remember, that's volts, electromotive force, right? We're going to see if we can get that into a derivative equation that's, well, you already got a derivative over here on the right. We're going to see if we can do something with this E dot dl here. And so that traveling wave that's going by, I want to look at the electric field. That's the one in the red kind of orange field that's in the vertical direction, as opposed to the blue magnetic field, which is coming into and out of the page. We're going to come back and look at the blue magnetic field here in just a second. Okay. Anyway, if I'm doing an integral like this around a closed path, well, I got to define a closed path. And so that's this black rectangle right here. Okay. And somebody decided, let's go counterclockwise around, because, you know, it's the way angles go in a polar coordinate system. So let's just go counterclockwise around. And the electric field on this side of that rectangle we're calling E. Okay. And we've moved some distance to the other side, just a small little distance, delta x, dx actually. And over here, the electric field is E plus some small increase in the electric field because I've moved a little bit to the right by some amount dx. And you can see it's basically right there to there. That's what happens to the electric field. It's gotten a little bit bigger by an amount dE. Okay. And so that's, I guess, what we would find. We would, if we wanted to find E dot dl over here, we'd start off with the value of the field right here. And we're making this little loop have some height dx right here. Okay, then I guess we come around this way. I started in this corner right here. I came up, I go this way. And you notice there's no term right there. I had the first term, that's from this side over here, okay? This side right here. There is nothing right here. There's no term corresponding to that. And hopefully you realize why. There is still a dot product right here. The direction dl or ds, which I'm always schizophrenic about, should I write L or S right here? Anyway, it's horizontal. The electric field is vertical. Those two directions are perpendicular. So across the top here, I'm really writing +0, right? Because E dot, whatever the displacement you want to call it, dl, ds, across the top is 0. All right, now I'm coming down this way. And we said over at that side of this little square loop, the electric field was just E. But notice I'm going around the loop downward to get back to where I started from right here. The electric field is upwards. That's 180 degrees. Dot product still is in existence. Cosine of 180 degrees, because the dot product deals with cosine, is -1. And that's why I wrote minus the electric field right there. Same height, same delta y for the loop right there. And then as I close around the loop, okay, I'm multiplying, I guess, whatever the value of the electric field is that's changing along there. But it doesn't matter because I'm moving in a direction perpendicular to the electric field. That dot product says there's also a +0 right there, right? And so it's really 4 sides to this thing. And you know, if you've never seen an integral like this, because Dr. Shelby hadn't talked about it. Is that her name? Shelby? Yeah, Shelby. Emerald. If she hasn't told you about those, that's how you do that. That's what this closed path means. I have to pick a path and I just integrate all around it. Okay. 4 sides to this path. We said before it was often a circle. That way we only have a circumference to deal with. We just have one equation, but this is what I would have to do. Anyway, what I think you should notice is E times delta Y over here and minus E times delta Y, they cancel. And so okay, internet connection. I'm stopped right there because my internet connection looked bad. All I've got left is that. Okay, so let's see. That's what I got left. That's the integral of E dot dl. It's just this thing right here. And so that's why from right here, I wrote that. Okay, it's just that coming right there. The other two terms canceled. Okay, and let's look at the other side now. Let's look at the rate of change of the magnetic flux through that same rectangular loop. Well, the magnetic field's all that's changing. I made the size of the loop, dx times d times delta y. Just made that d because it's infinitesimally small. This, who knows how big delta y is. It really doesn't matter. But point is, that came right there. And why it doesn't matter, that height delta y is on both sides. And then with impunity, I brought that over to the other side of the equation, and I got the derivative of the electric field with respect to x is equal to the negative of the derivative of the magnetic field with respect to time. Now, that's a kind of a wacky equation right there, particularly if your differential calculus always had you only dealing with one variable. Because clearly here we got two variables in play, the electric field and the magnetic field. Apparently in this problem, our functions not only of x position or of time, they're functions of both. And that is the reason for multivariable calculus, right? I got two variables there. Both of these two things vary with both position and time. We knew that. We knew that back in chapter 13 and 14 when we were talking about mechanical waves. And now I've got this equation that absolutely puts them together, okay? And shows the relationship between the two. So how one varies in space, the other one varies in time, and they're almost equal to each other, and they have a negative sign in between them. All right, so that's Faraday. We're going to look at the blue part of the curve, the magnetic field, with Ampere here in a second. We're going to do exactly the same thing. Okay, I've got the magnetic field on this side is B. The magnetic field on this side, notice I've drawn the loop with the magnetic field here. That's going to be B. I guess it's gotten bigger, plus dB. Yep, so I'm a little bit bigger on the other side. Okay, and I'm going to do the integral of B dot dl exactly like I did. I guess I'm starting right here in that little corner and coming around the loop. So the first thing I do is I multiply B times the height. Now, since this is in the z direction, that's why I used z, whereas before I was in the y direction, vertical. Okay, so B times delta z. Okay, then I come across right here, plus 0, for exactly the same reason. The magnetic field and the displacement there are perpendicular, so plus 0. And then around, as I come this way, the magnetic field is in the positive z direction, and I'm moving as I trace around this loop in the negative direction. So that is the cosine from the dot product of the angle between them, which is 180 degrees. Cosine of 180 degrees is -1. And then I just took the magnetic field at this side, B plus delta B times the distance. And just like before, plus 0 over here, because when I come back to where I started from, as I do the integral around the closed loop, okay, it just adds 0 again, and I'm back where I started from. So I have gone around a closed loop. The magnetic fields, thankfully, were constant. So these integrals right here just became a B times a length, just like E times the length before. All right, if you look, something's going to cancel here, right? That's a positive B times delta Z. That negative sign makes this a negative B times delta Z. I don't really want to cross that out. I still have dB times delta Z with the negative sign. So those three pieces come together right there. And that's, I guess, what I'm writing for the integral of B dot dl minus the result I just got right there. On the other hand, let's look at what the rate of change of flux through is there. And notice the electric field is going up. So yep, it absolutely is going right through that, right through the area bounded by that loop, isn't it? And I'm doing exactly what I did before. I'm saying the rate of change of the electric flux is just the rate of change of the electric field times the area of that loop. The area of that loop is dx dz. Okay, so that goes right there. And of course, I got to multiply by the appropriate constants. I think I'll just finish this. This will be cool. It'll be good timing. All right, so I'm looking, and that means these two guys right here have to be equal to each other, because that was that, which went right to there. Okay, and again, how high I made that loop, how big I made that loop, didn't really matter. Didn't really matter. With impunity again, I'm bringing that guy over to the other side of the equation. Come on, mouse. I'll move my mouse pad here. That guy's coming to the other side of the equation. So I got the derivative of the magnetic field with respect to time. I brought the negative sign over to the other side here, and it's the rate of change of the electric field being left over here. Again, magnetic field and electric field are related. Okay, they're related with the derivative of the magnetic field with respect to x. Remember, magnetic field varies with both x and time, is equal to how the electric field changes in time, and the constants are right there. Okay, so let's put those two together, those two ideas. Ampere's law and Faraday's law written as derivatives. Now, those of you that had multivariable calculus knows that there is a kind of a technical detail right here. It's notation as much as anything. When the fields are both function of position and time, this kind of derivative is the thing you do when you're only taking a derivative with respect to one thing. Notationally, you write a script D. It's called a partial derivative. And all it means is when I'm taking the derivative of the electric field with respect to x, this notation reminds me, just hold time constant. On the other hand, when I'm taking a derivative of the magnetic field with respect to time, this notation says, just hold x as a constant. Functionally, they work exactly like regular derivatives. We just recognize that since E and B are both functions of position and time, that when we take a derivative like this, we really want to remind ourselves when we take that derivative, hold time constant. When we take this derivative with respect to time, hold position constant. Okay. In any event, let's kind of put these two guys together here, I guess. Oh, let's see. I have, this came from change of magnetic field, Faraday's law. This came from Ampere's law with, this is all the displacement current correction, right? That wouldn't even be there for what we talked about at the start of class wasn't in effect. If Maxwell hadn't come along and found that displacement current to replace regular current, we wouldn't even be talking right now. In any event, we've got these two things. I write them as partial derivatives. What I want to do is take the second derivative of this guy, take a derivative of that with respect to x. Okay, and so that became the second derivative of the electric field with respect to x. Cool. All right. Well, I have to do the same thing to the other side, minus the derivative with respect to x taken on the derivative of the magnetic field with respect to time. That's okay. You just do them one at a time. You do the derivative with respect to time first, then you do the derivative with respect to x. On the other hand, I want to take this guy, which came from, I guess, from Ampere's law. I want to take the derivative of it with respect to time. And that becomes a second derivative over there. Look at these two guys in the middle. Look at these two guys in the middle, okay? They're almost the same, just the order is flopped, isn't it? Which way you take the derivative, all right? You can either believe me or you can check it out. I'll give you as many functions as you want. It does not matter whether you take the derivative of the magnetic field first with respect to position and then time, because you're holding time constant when you take the derivative with respect to position. Or on the other hand, if I take the derivative with respect to time first, holding x constant, and then take the derivative with respect to x, you'll get exactly the same answer. So these two guys are equal to each other. Well, that lets me cancel those negative signs. And the second derivative in space of an electric field is equal to the constants that were left behind times the second derivative of an electric field with respect to time. We call that a wave equation. Notice what I've managed to do here is I eliminated the magnetic fields from these two equations. I could have gone the other way and eliminated the electric fields in favor of magnetic field. I would have gotten a wave equation that way. But like I said earlier, people tend to work with the electric field. It has a bigger magnitude, okay? Just the numeric value is bigger. This is called a wave equation. Called a wave equation. And in 2 seconds, I want to propose a solution, okay, and show you what happens. Show you what happens. Wouldn't be surprised at all if this was a solution, because when we talked about mechanical waves, we said something like a mechanical displacement times the sine of that thing called a wave number times x minus the angular frequency times time was the solution for wave on a string or a slinky or something like that, okay? It wouldn't surprise me at all if we had the exact same functional form for a solution. I never derived a wave equation for a wave on a string, but it would look exactly like this with just a different set of constants. It would still be a second derivative with respect to position and a second derivative with respect to time. All right, the great thing about this is we can take that derivative twice and get an answer, okay? Let's see. when I take the derivative with respect to x, the first thing it does is bring out a k from the chain rule, and then I just change the sign to a cosine. When I take the second derivative, that cosine gets changed back to a sine, okay? And brings that negative sign in. On the other hand, if I take the derivative of this thing with respect to time, the first thing I bring out, it changes sine to cosine, okay? And I bring out a minus omega. And then when I take the derivative again, it changes from a cosine, it changes back to a sine, and I brought out omega twice. And so these are the two derivatives. I'm going a little quick right now because I'm running out of time, but I do want to point out that you can check these and you should find that those are the derivatives you take. Remember, when you take a partial with respect to t, just make x a constant. Just pretend it's a constant. When you take a derivative with respect to x, just make t a constant. Anyway, if you buy those two things, you'll see what I've done is I've substituted in the answer right here. I substituted in the answer right here, and those are my two constants. Of course, there's a negative sign on both, so they cancel. And in order for this equation to be true, k times E0, k squared times E0, has to be equal to omega squared times E0 with those constants. I guess I can cancel that. I really can't cancel that because it could be 0 and that'd be divided by 0, not allowed. But it is true that k squared must be equal to these constants, permeability of free space, permittivity of free space, omega squared. And so I just rearrange those things, right? Those constants right there have to be equal to those constants right there. That's what I'm saying. If I rearrange those two guys, I go omega squared over k squared is 1 over the permeability of free space, permittivity of free space. And remember, just a few slides back, we said that was the speed squared, didn't we? That was the whole point of showing you that little review. And so apparently the speed of light would just be, okay, it's what we talked about a couple slides back, 1 over that. Now here's the kind of the factor I have. If I take 1 divided by 4 pi times 10 to the minus 7th, and that was Newton per amp squared, and I take 8.85, oops, I need 8.85, sorry, that's just a big period now, times 10 to the minus 12th Coulomb squared per Newton meter squared. If I put those numbers in and take the square root, what do you think I get? Almost phenomenal answer, because just as Maxwell is doing this calculation and he's figuring out this relationship and he's figured out that electric fields and magnetic fields are this thing we call electromagnetic radiation, other folks, Michelson for one, a Naval Academy guy, we're all proud of him. He didn't win the Nobel Prize for this, but he was making these measurements. He's coming out with a number very similar to 3 times 10 to the 8th that Maxwell is developing theoretically. Something I've said before, anytime in science you have a theoretical result verified by experimental results, so Maxwell's theoretical results, Michelson's experimental results, and they come together and predict the same thing, you've got a theory that's been it's kind of matriculated up to being a law now, and we can believe it is as part of science. And so I just wanted to leave you with that here today. Sorry I went a couple minutes over, but it's for me such an aha thing that I take two numbers that I've been using to calculate electric and magnetic fields throughout the course of the semester. They have absolutely nothing to do with traveling light, electromagnetic radiation, X-rays, AM radio. It has nothing to do with that, but apparently it does, because those two numbers predict accurately what the speed of electromagnetic radiation is. We'll call it a day. We'll pick this up back on Friday. I don't have time to go through the worksheet with you. I was going to get you started. I will do office hours today again at 1:30, and I think that's all we got. So I'll stop sharing and say everybody have a great day, and we'll talk to you later on.